So this talk is about the implementation of neural networks on fixed point architecture. It's a joint work with Dorra and Khalifa. Okay, so very quickly, the problem is quite simple. It's just like to put a bull in a China shop. So the bull is the large neural network, and the shop is a little embedded system, either a microcontroller or FPGA. Okay, and as you know, neural networks have more and more parameters, millions currently or more, and so the difficulty is to fit them in these small architectures. So what can be reduced? First, people do pruning, that is, they remove some weights. This is not, it's a very interesting topic, but this is not what I'm going to do to present in this talk. The second solution is to reduce the size of the weights, that is to play with precision. And again, there are several ways to do it. You can either reduce the precisions of all the parameters, using, for example, 16 values on 16 bits or even less. You can also do mixed floating points precision, and there is a lot of libraries integrated to Tensorflow or to the other libraries to do that. And a third solution is what we are going to see in this presentation, is to use fixed point arithmetic. Actually, when you use fixed point arithmetic in the implementation, it's only integer numbers, and so it's far more easy to handle from a hardware point of view. You have, it's faster, you use less memory and energy, but you have the price to pay is that it's more difficult to generate the code. So this is what we do in this work, and another originality of our work is that we have error thresholds which are guaranteed. That is, we can guarantee by our method formally that the error on the fixed point network is less than some bound given by the user compared to the original network. Okay, so how do we do that? To give you an overview, we have, so it's done inside a tool called Poppins. There is 5 main steps in this tool. First, we take a TensorFlow model and we extract it. We make our own intermediary representation. We extract the weights and so on. Then we need to know the ranges of the variables of the value inside the network at each point. So we perform a range analyze. Currently, it's an under approximation computed dynamically. We execute several times the network on the input set, and we compute the convex hull of what we obtain on the result. Ideally, it should be a static analyze. But it's difficult to implement a very accurate static analysis for this. And next, once we have these ranges, we generate a set of constraints. For those who know, it's a MILP, mixed integral linear programming problem that we have. So it's a set of equations. I can see it there. It's a set of equations of inequalities between linear expression among integer quantities only. And there are min and max, so it's not a pure ILP problem. Okay, so in practice we give this system of constraints to Z3, but we could use another solver. And once we have the answer, we use it to generate a fixed point code. So the the outputs of the constraint subsystem are the precisions that we must put for all the weights and all the intermediary results computed by the neurons. And we generate these fixed code using, currently we use the fixed math library to do that, but we are working on a new implementation where we use the AP fixed library because we want to generate FPGA code using VTs. Okay, so this is what we generate from the original TensorFlow model, and the difficulty is to find the formats which are somewhere in the operation. This is a cast from one fixed point format to another. The difficulty is to find this value, and this is what we obtain from the system of constraints. Okay, so in details, how does it work? Well, it's rather technical. It is detailed in the paper. Just to give you an intuition, I will only present this for fully connected layers, but there are other layers introduced in the article. So a fully connected layer computes some output y in function of the weights of the network W and of inputs x. Okay, and we can compute the error. We can bound the error on y in function of, I'm not going to detail this expression, but in function of the maximal value of entries, the maximal value of the weights, and the maximal errors on the weight and on the entries. This is the four parameters of this equation. And knowing also how the errors can be propagated in the fixed point arithmetic, we can deduce from all these constraints which say that the precision of some neuron must be greater than this equation in which we find the accuracy of the output, the accuracy of the most significant bit of the inputs, and some static parameters. So we generate constraints like this. We are going to put a threshold on the last layer, the outputs of the network, and going backward with these constraints, we will compute the accuracies of all the neurons in the intermediary layers up to the input of a network. Okay. There are theorems in the paper and proofs of all these formulas. Okay, and so we can do it for all, for a certain number of layers, and using these, taking a neural network, we can generate a full system of constraints for it. Okay, so as I mentioned, this is implemented in the Poppins tool, and we have experimented on a certain number of networks, going up to 10,000 parameters. Okay. The first graphic, I like this one. It's interesting. You have on the x-axis the accuracy threshold, which is required by the user. So we want to have 12 correct bits on the output, or 11, so on. And in green, it's just the threshold. The accuracy is on the y-axis. So this is just the function 2 to the power minus x. So it's the accuracy threshold. If the measured accuracies is above the curve, then there is a safety problem. Our method is not safe. To be safe, we have to be below. But if we are too much below, it means that we do not have optimized enough the system, but the goal is not to have the most accurate network. We want to have the network which consumes the less resources as possible, so the worst network, which stays below the yellow curve. So we want to approximate the yellow curve by below without being never upper. And it's rather the case in these representative execution, examples of executions. On the right, you have a measure of CPU and memory used by the fixed point, the second is timed the second bar, and the floating point execution. So it's rather the same there. But when we go to microcontroller, here it's a STM32 microcontroller. Well, we can see that we use far less resources in fixed points. On the left, it's the time, and on the right, it's the energy consumption. And more importantly, there are several networks from our benchmark that cannot pass in floating point. We cannot load them and execute them on the board. It explodes. But we can do it in fixed points. Okay, so I will conclude very quickly, just to say that we want to add more layers and to our tool to compare. Difficulty for comparison is to have methods with formal bounds. We want to mix pruning and quantization and go to FPGA. And our goal would be to be able to embed segment. Here is an example of application. It's a semantic segmentation using a neural network and a UNet. So this is the kind of network that we would like to put on small embedded system. Thank you for your attention. Yes, this is the accuracy threshold set by the user. I say I want to have 6 or 8 bits correct on my results. And this is the measured error on some executions. So the threshold is, if I want to have 9 bits, so the error must be less than 2 to the power minus 9. So this is the green curve. So if I am above, I am wrong. I must be below. But if I am too much below, it means that my system is not optimized. That if I use 100 bits for all the computation, it's easy to be below. The goal is to stay below using the less number of bits as possible, so as few bits as possible. So I want to fit to the curve by below while never passing it.
Actually, I couldn't understand the y-axis.
Okay.
But let's take it offline.
Hello. You really impressed me in the constraint solver, and I'm also doing some works in the fixed point arithmetics. And I would like to know if the constraint solver was executed statically or it's run on a sampled input.
No, we consider ranges of inputs. So the constraints are computed for the worst case of all the range of input that we consider.
Okay, thank you. And I am wondering if is the layers weight being replaced with fixed point or
if the layer? Okay.
Oh, the layer. Okay, thank you very much.
Can you repeat, please?
I am wondering if is the layers weight being replaced with the fixed point or the inputs?
Yeah. Both
all of them?
Yeah.
All of them. Okay, thank you.
Thank you so much.